Panda, and this is a video for with the preview talks for the network function session at SIGCOMM 2020, which is session 11. Let's start by asking what are network functions and why do we need them? In textbook definitions of the network is responsible for only providing best effort delivery. What in particular this means is that Sally can send packets destined for Google, and the network's job is to forward them along a path to Google. The important thing to remember here is that Sally decides what packets to send by running some application or program. Google decides how those packets are processed by running some program. The network has very little control beyond the ability to just forward those packets to Google or drop them. In reality, we want a lot more from our networks. We use them for a lot more things, and we have been spending a lot of money on them. In particular, companies like Verizon or system administrators like John want the ability to control what traffic is being forwarded and how is it being forwarded. What do I mean by they want the ability to control this? So one way to look at this is that network operators would prefer to not have their networks be used for carrying malicious traffic, which doesn't help anyone and only causes people unhappiness. And they have turned to things like firewalls to avoid this problem. Similarly, when possible, they want to minimize the amount of traffic that's being forwarded, so they want to be able to compress it. They want to avoid having people like the NSA spy on you, so they want to encrypt it, and they might rely on proxies to do this. They also increasingly want to provide value-added services. For example, they realize that many of their customers watch Netflix and they want to give them the best Netflix experience, reduce the amount of time until someone can start binge watching the next show, and they do so by providing caches. Similarly, they realize that a lot of the services are important to people and they want to improve resilience, and this is something they do by installing load balancers and similar devices. Now, the important thing about all of these is that these services that I'm talking about that the network provides, it goes much beyond forwarding. You actually need to modify packets, create new packets, etc. And these services are usually implemented by things called network functions, and that's the nature of what we're going to be talking about in this talk. Now, you might ask, okay, those are some interesting services. Why did people want to provide them, and why did it come about? Well, one reason why everyone wants to provide them is, of course, because of money. You can charge for these additional services. But the other is it improves user experience, which gets you more users on your network. And as a result, this has become, NFs are widely used today. So, this is an important part of the internet and the network ecosystem. But the problem is, as we adopt NFs, they also have challenges. In particular, the performance of a single NF can impact the performance of the network by slowing down certain packets. Failures of an NF can cause failures in the network because some users' packets are suddenly not being forwarded. Bugs in the NF can actually look like bugs in the network. And so the papers in session 11 that we're going to be talking about right now try to address these issues. Okay, so let's go on to the papers without much ado. So the first paper that we're going to be talking about is fault-tolerant service function chaining. This, of course, based on the fault-tolerant word, is trying to make sure that the network can survive failures in an NF. But to understand it, let's start by looking at what is the service function chaining. So service function chaining is this idea that a user like Alice doesn't just want the functionality of one NF, a firewall, but she often wants multiple things to work in concert for her. She wants her packets to be firewall, she wants to go through a NAT so she can share her IP address with others, and she wants them to be encrypted by a TLS proxy. Service function chaining is a way to compose the functionality of multiple NFs together by having packets go from one to another. Okay, what does this have to do with fault tolerance? Well, to understand this, let's look at how network functions have been made fault tolerant so far. So there's been a lot of work on how to make fault tolerant network functions appear. The one approach to this has been to use active replication, run n copies of the same NF. This, of course, increases the number of resources you need. Another approach has been to use VM or process checkpointing to store the state of the NF, and then you can restore it when there's a failure. The problem is checkpointing requires some amount of coordination, which adds to the performance overheads. The last approach is record and replay, where you use loggers at the ingress and egress of the network function to record the order in what packets were received and the order in which they were processed. And then when you have when the FDNF fails, you can replay the logs and recover that state. This of course has the problem that recovery time is now bounded by how long of a log you have to replay. And there have been works that combine all of this. Most recently, Justine Sherry and others in SIGCOMM 2015 presented this work, Fault-tolerant Middlebox, and what it did is it combined checkpointing and record and replay to give you the best of both worlds. The paper Fault-tolerant service function chaining builds on FTMB. Now, what the authors point out is, okay, if you took FTMB and naively applied it to a service function chain, there's a lot of redundant work happening. Why? Well, remember, you have loggers at the ingress and egress of all network functions, and a lot of this information being logged here is redundant. Also, you're taking a bunch of these snapshots and having them send them individually while, and this is usually sent over the network, and by being a little smart about it, you could save this. So what the authors propose is the following. They say, have the NFs in the chain act as loggers for each other and have them store the NF for each other. What this does is it moves these logging feature into the next NF in the chain. And what the authors show is that by doing this, they get significant performance improvements. You should read the paper for more details, but the basic idea is by recognizing that things are chained, you can remove redundant elements in the network. Okay, that sounds cool. But if you actually look at it, the paper has many interesting ideas, one of which is a common problem with record and replay strategies, is we need to understand what is the order in which packets are being processed, even though packet processing is often concurrent. The authors propose to use transactional packet processing. Now, this is an interesting idea that we haven't seen in other contexts. So one question that you should be asking yourself as you look through the paper is, why is it possible to use transactional packet processing here, and should we extend it? Should we use it in other places? Why only use it for service for fault tolerance? The other question that's worth asking is, what happens if the chains that we're considering are not quite so simple? What if they're branchy? How do we deal with them? Similarly, what happens if NFs that are chained together are on different machines connected by a lossy network? What happens with packet losses when chaining? These are things that you should ask and consider as you read the paper and attend the talk. Next, the next paper we're going to talk about is Gallium, which is automated software middlebox offloading to programmable switches. So middlebox is just another term for network functions. Software middlebox are exactly what we've been talking about. So how are these network functions built today and how are they deployed? Well, they're programs that run on servers, and in particular, people have worried a bit about the I/O performance of servers, and so you often use kernel bypass libraries like DPDK, NetMap, and XDP to improve the I/O performance. But at the end of the day, processing is carried out on the CPU, which is very general, and it gives us some of the generality we desire when building NFs. The problem, of course, is CPU performance can be low in certain cases, and as a result, we've had the emergence of programmable switches and PISA architectures where programs with limited expressivity can be run much quicker than they can be on CPUs. And the question this paper asks is, hey, can we combine these PISA architecture programmable switches with CPUs to get both generality and better performance? Can we improve the performance of NFs by using programmable switches? Now, remember, we're combining the two, which means that some amount of the logic is going to run on the server and some amount of the logic is going to run on the switch. So the question, of course, becomes, how do you partition the functionality of an MNF between these two parts? How do you decide that? And that's what Gallium does. Gallium is an automatic compiler that does this partitioning. So what you do is you feed Gallium with a C++ program. Gallium uses LLVM and runs a bunch of analysis passes, and at the end of it, it produces a P4 program that you can now compile and execute on the switch, and it produces a binary that you can now run on the server. And in combination, these implement the same semantics as the original C++ program. So given an NF, you have now produced two programs that implement the NF functionality. Now, the questions you should ask yourself is, hey, obviously we're offloading because we want to run as much as possible on the programmable switch. How do the authors maximize the amount of computation offloaded? Are there more opportunities there? Similarly, compilers depend on static analysis. What are the limits of static analysis when they're trying to decide what should be offloaded? And finally, what is the cost of offloading to the switch versus what is the benefit that they're getting? On a related vein, there is a talk in session 7 called TEA, Enabling State-Intensive NFs on Programmable Switches, which asks the opposite question. Suppose we wanted to run general-purpose NFs on programmable switches. How can we extend them to run this? And in particular, the focus here is on state. I recommend you look at the paper and look at the preview session for session 7 to learn more about this work. Okay. Moving on, the next paper we're going to talk about is contention-aware performance prediction for virtualized network functions. So remember in the last, for the Gallium paper, I told you that NFs are actually run on servers. Now, server CPUs have, for the last 2 decades or so, been multi-core CPUs, and as a result, lots of people are actually running several NFs on a single server. What this paper asks is the following. Suppose I'm running multiple NFs on the same server. Can I predict the performance of each NF? Can I predict how many packets it can forward? Why do we want to predict the performance of an NF? Well, we need to predict it for provisioning. We need to know how much traffic we can process in order to know how many servers we need to put into our network. Okay, why is it challenging? It's challenging because even though cores appear isolated to us, in reality they share some things, including the I/O controller and the I/O bus, and the memory controller and the memory bus. And contention on these things, so contention on shared resources, can allow one NF to affect the performance of another. Okay, so this is a problem that has been known for a while, and there have been a few approaches trying to address this. One of the early approaches, which was by Dubrescu et al. In NSDI 2012, said that, hey, you know, most of the contention that we worry about comes from the memory and cache, and they built a linear model around the memory and cache to look at the source of contention. More recently, in NSDI 2018, Rescue built a more complex model and also used an isolation technique, but at the end of the day, both of these focus on memory and cache and use a linear model for the prediction. The authors argue 2 things in this paper. The first is they say looking at just memory and cache is insufficient. Other things such as the I/O bus can matter. And the second thing is that the linear models are insufficient. So the way the authors address this is they expand the set of features they consider. So they consider 600 performance counters that are accessible from the CPU, and they use gradient boosted regression to then compute a more complex model from these 600 performance counters. Okay, this is great. They show that this gives us a more accurate model in their test cases, but as you're reading through this, the question you should ask is, remember, the entire premise of this paper is that previously we were looking at a smaller set of features that were not sufficient. Well, okay, why do we think these 600 features are sufficient? Why shouldn't there be another 600 that we are not looking at because the CPU doesn't expose them? Similarly, another argument was that linear models are too simple. Well, if linear models are too simple, how do we know gradient boosted regression models are complex enough? Why shouldn't it be more complex than that? These are some questions you should think about as you look at this paper. And this brings us to the last paper, which is a debugging paper called Microscope, Queue-based performance diagnosis for network functions. So the problem is this: we have these NF chains, we talked about them already, and consider a case where you decide that, hey, for some reason, some packet P is taking a really long time to get across this VPN. Let's say, you know, normally most packets take 10 milliseconds, but this one happens to be taking 100 milliseconds. And what you want to understand is, why did packet P take 100 milliseconds? As an operator, you need to fix this because 100 milliseconds is unacceptable. Okay, so now as you try to understand this, what are the possible sources of this 100 millisecond delay that packet P encountered? Well, one problem is that the VPN is misconfigured. Packet P tickles the configuration wrong, and that's why you get bad performance. So that's one problem, and that you can blame the VPN and fix it. But the other problem is that the NAT is actually what is misconfigured. So what happens is, even though the NAT receives, let's say, 60 packets per second, it only forwards packets once every 10 seconds, and so it forwards 600 packets every 10 seconds. This is called a burst, and the VPN, on receiving this burst of packets, has to process them and is slower than you'd expect, and this shows up as latency. The same thing could be happening from the monitor. Microscope is an attempt to try and identify the root cause of such a problem. So how does Microscope work? Microscope recognizes that in front of every one of these NFs in software, there is a queue. And most packets are either being processed by the NF or they're waiting in the queue. And if we can discover whether a packet was waiting in the queue or a packet was being processed, we can differentiate between whether the packet was slow because the VPN is misconfigured, or so if the VPN is misconfigured, then it should show up as processing time. While if it received a burst, it should show up as queuing time. And by distinguishing between this and applying this process recursively, Microscope is trying to identify the root cause. So how does this work? So for each packet, or for any packet that's being considered, Microscope asks, hey, how much time did the packet spend at each queue, and why did it spend time at each queue? By identifying this and comparing it to all other packets so for example, if you consider packet P and packet P spending some time here, and you consider another packet P prime that behaved well, Microscope asks, what is the difference between P and P prime that caused P to spend more time at a particular queue? And by understanding this, they can identify the cause of the bug. There's a lot of equations and a lot more details about how this is done in the paper, so you should really look at that if this tickles your interest. But as you're reading through that, the question that you should ask for this in any measurement-based technique is, what is the resolution that this measurement technique gives us? In particular, what assumptions did they make to make the technique work? Does it work in, for example, very noisy environments, such as ones where the VPN naturally has very, very wide variance in how long it takes to process packets? Does it work in cases where the behavior of the NF is bursty? So we know that there are NFs that are naturally bursty. Does it work in that case? And what would it take to relax these assumptions? Because by understanding this, you'll understand where the limits of Microscope are, how those limits are being used, and how to extend this work. I hope this gave you some idea of what's going to come in session 11. I will be in the Slack, and so you can certainly ask me any questions that you have in Slack, and I look forward to seeing you at this session. Thanks. Bye.